All right, so we're about to start our next sections. I'm going to do two sections in here. We're going to go through fundamental counting principle, and then we're going to go through permutations without restrictions from your workbook. So this is the beginning of our new chapter. This is the last unit in our course. This unit sometimes is called permutations and combinations. It's sometimes called counting methods. It's sometimes called combinatorics, depending on who you're talking to and what they're referring to and whatnot. But it all refers to the same stuff. Most commonly, you kind of hear of it called permutations and combinations. And these are but this is kind of a very different topic in this course, and it ends up looking very different from any of the other things that we've done in this course. For the most part, it is not going to be very algebraic. It's going to be quite numerical. And so the whole thing with transformations and how we spent so much time on trigonometry and how transformations really apply to everything else that we've done in this course so far, they don't really apply to this at all. And so this ends up being quite a different thing. A lot of students find that to be kind of refreshing, that we have this change, that we move on from that previous stuff in an entirely new direction. Some people find it refreshing because you get to start from zero again. So that ends up being kind of a nice way to finish this course off. So we'll start off calling this the fundamental counting principle, and let's get at her. What this starts with is it starts with saying, okay, so if you have a task that has a few different steps that you have to partake, so you have to go from home to school, and then from school you're going to go to work after school for a couple hours, and then from school or then from work you're going to go to your friend's place on your way home. And then if you want to start to count how many ways you can get that job done, how many different ways you can get to school, how many ways you can go from school to work, and so on. And so if you have these individual steps that you can take, if we take it down to something that ends up being very pretty simple, if we look at something like you're at home, if there's 3 different ways that we can get to school, and then from school there's 2 different ways that you could get to work, and work to your friend's house, there's really only just one way, but to get from your friend's house back to home, so there's 2 different ways. Then how could we count how many different ways you can make this whole path, this whole route, this whole trip? And it ends up being kind of complicated to actually count it out, to think, okay, well, if I go along Sun Valley Boulevard to get to school, then I'm gonna, and then I get to work by taking this, whatever. It ends up being kind of arduous to count all of the different ways up. But if you think about that, you only have 3 ways to get to school, and then 2 ways to get to work. And if we simplify it down to that's really the only piece, then this ends up being just a product of 3 times 2 different ways that you can get from home to work. And we could count them all out, and you could think, okay, so is there really 6 ways? I'm going to go 1 way through this path, 2 ways is going to be that path, and then maybe I'll use a different color for this second way to school. So this is number 3, this is number 4, and then you can kind of quickly see that here's number 5, and then that's number 6. So there are 6 ways of getting to work. Well, then if we complete the rest of the trip, it just ends up being times 1 for getting to your friend's house, and then times 2 of getting back home. So it ends up being a product of all of these things, a product of all of these choices of how you complete these tasks. And that's what we call the fundamental counting principle. So it tells us here, if a task is made up of a series of individual steps or choices, then the total number of possibilities for the task is given by multiplying the number of choices for each step together. If m is your number of choices for the first step, n for the second, p for the third, and so on. This is given by m times n times p times dot, 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 because you can have as many steps as you really need in here. How would you create an outfit from 2 pairs of pants, 3 shirts, 4 pairs of shoes? How many different ways can you get dressed in the morning? Okay, so as a tree diagram, so this ends up being just kind of a visual way. And if you have pants, you have 2 different pairs of pants. So this is you getting dressed in the morning. You can either take that pair of pants or this pair of pants. And then once you've decided which pair of pants, now you have a shirt to put on. And for each pair of pants, you have 3 different shirts. And you have, say you have a pair of jeans and you have a pair of khakis for pants. Then if you've put the jeans on, then you have a blue shirt or a white shirt or a black shirt. And then a blue shirt, the white shirt, or the black shirt. The same 3 shirts end up being your branches in the next branch of this tree. This starts to get pretty clogged up, and there's lots going on here. If I have 4 pairs of shoes to decide between, now each of these branches have 4 branches coming off it, and we quickly start to run out of room. I'm only halfway done this tree, and it looks like I've gotten 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of these ways of getting dressed in total. And that was for the pair of jeans. How many ways for the pair of khakis pants? Well, it would be another 12. So altogether, this listing, each line ends up being a line in it's called our sample space. And we would have 24 different ways of getting dressed. So to draw it out visually, sometimes it's going to be beneficial. But in this case, it's probably easier just to kind of think of it as a fundamental counting principle issue where you have, we're going to have a blank. And we're going to, in each of these blanks, so this is going to represent your pants. This is going to represent your number of choices for shirts and your number of choices for shoes. Okay, so all that we end up with is we have 2 for pairs of pants, we have 3 choices for shirts, and we have 4 choices for shoes. If I multiply all those together, I get 24. So really that's kind of the bigger idea of what's going on here, is accounting for all of your choices and then just multiplying them together. That is what the fundamental counting principle says. So number 2, how many different license plates can be made that consist of 3 letters followed by 3 numbers? 3 letters, you need to know that in our alphabet we have 26 letters in total. Numbers, the numbers from 0 through 9, there are 10 of them. If you count 0 as a number, and it is. So we have 10 different digits, 26 different letters. How many different license plates can we make? If we've got 3 letters followed by 3 numbers. So letter, 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 number, number, number. So we're going to have 6 blanks here to describe our choices. And these first 3 end up being letter. It says there's no restrictions. Well, other than the fact that in the first part of this question, it said that it's going to be 3 letters followed by 3 numbers. So the first 3 are letters, the next 3 are numbers. How many choices do we have? We have 26 choices for the first letter. Once you've figured out what that first letter is, now we have 26 choices for the next letter. Once we've figured that out, then there's the third letter, and again we have 26 choices. For the numbers, in each slot we have 10 choices. So when we multiply this out, this ends up being this huge, massive number, 17,576,000. different license plates that we can make that go letter, 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 number, number, number. Now, when we talk about restrictions, that will often be one of the things that one of our first wrenches that we throw into these questions is if there's no repetitions allowed, it's still going to be letter, 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 number, number, number. And we still have 26 choices to make for that first letter. But once we've chosen that letter, I don't know what letter it is. It might be an L, it might be a K, it might be a Z. But once we've chosen what that letter is, we now only have 25 choices left for the next letter, and then 24. So we are going to be multiplying this amount that is decreasing, 26 times 25 times 24. Times, now for our digits, we have 0 through 9, so we have 10 digits to start with. Once we've placed one down, once we've picked a digit, then we only have 9 for that next spot, and then for our last spot, we have 8 choices for this. When we multiply this together, this ends up being 11,232,000. When you're writing large numbers, please don't use commas between groups of 3. We use a space in between groups of 3. All right, question number 3. Determine the number of 4-letter arrangements that can be made from the word English if no letters can repeat and there's no further restrictions. So we have these letters, E-N-G-L-I-S-H. We want a 4-letter arrangement. And how often we want to think about this is when we see the word arrangement, if we want to think of these as Scrabble tiles. Because it's an arrangement, that infers that we can't use the letter again. And you know of the game Scrabble, the old school game with all those little wooden tiles. And it'll often be pretty helpful for us to think of these letters as that, especially when it tells us that we have an arrangement. That infers we can't repeat letters. So we have 1, 2, 3, 4, 5, 6, 7 letters in the word English. So you have 7 choices for that first letter. Once you've selected that letter, once you've put it down in place, then we have 6 choices. Then we have 5, then we have 4. Fundamental counting principle tells us we are going to multiply this all together, and we have 840 different 4-letter arrangements of the letters from the word English. All right, so when we talk about restrictions in this unit, we want to deal with the restrictions first. And our first letter must be an E. If that first letter has to be an E, it's not quite correct to say that we have no choice and 0 choice about what that is. We actually have 1 choice. There's only 1 letter that can go there. Yes, it's true that you have no choice. It must be an E, but think of it as a 1 because we're going to be multiplying it. So we put that letter E there. Really, the only choice ends up being with the rest. Once we've selected that to be an E, then we have the rest of it can be anything. So this can be 6, and then 5, and then 4 different choices for those second, third, and fourth letters. Multiplying that together, this is 120. Now, question C, the first and last letters are vowels. When we talk about vowels versus consonants, A, E, I, O, and U are letters that are voiced, whereas consonants are letters that are not. So everything else in this word of N, G, L, S, and H, but we have an E in this word, and we have I in this word, and there's no. So those are our 5 letters. The vowels are the E and the I. The whole argument about whether Y is a vowel or not is Well, is tomato a fruit? Is Y a vowel? I don't know. It depends on who you ask. On a diploma exam or any other test, it would be made. You either wouldn't have Y in the question like we don't have here, or it would be clear about what we mean by vowels. So in this case, we don't have Y. It doesn't really matter. E and I are our vowels. Now, we have a 4-letter arrangement. The first and the last must be vowels. So really, we only have 2 choices for that letter. So we deal with the restrictions first. That says we have 2 choices for that letter. That means the back vowel, we only have 1 choice because we've already selected that first one to either be the E or the I, which means the second one, the last one's going to be either the I or the E. Now, once we've placed those down, now we have 5 choices because there's 5 consonants. They can't be a vowel. Even if we had another vowel in this word, if this was the word Englisho, if this was the word Englisho and we had another vowel in here, it would start with 3, then we'd have 2. But I suppose the fact that it says the first and the last letters are vowels, it wouldn't state that those had to be consonants. This is just going to be all of the letters remaining. So in this case, it's 5 times 4, and we multiply this, and this ends up giving us 40 different words. But these questions start to get more complex. And the word must contain a G. There's a number of different ways of looking at a lot of questions in this unit of how we would do it. One way is to think, okay, if the G is the first letter, we have 1 choice for here. The rest of the word ends up being 6 times 5 times 4. This is a separate question. We no longer have this vowels restriction for the first and last letters. It's just saying, what if the word contains a G? So either the G is at the first letter, or when we look at different cases of things happening in combinatorics, we are going to add those cases together. So either the first letter is a G, or the second letter is a G. In case that would be your 1 there. The other letters, 6, 5, 4, we fill in around it. Or the third letter is a G. That means we have 1 choice for this. 6 times 5 times 4 for the rest. Or the last letter is a G. 6 times 5 times 4. We end up with 480. But there's more than one way of doing this. We could have looked at it like this. Let's just place my non-G letters. And we have 6, 5, and 4 for all of those letters that aren't G. And if we put those down in that kind of order, now, where could we place our G? We could place it at the start, or in between the first and second, or in between the second and third, or we could put it at the end. So it's like we have 6 times 5 times 4 times 4 different places where we could put that G. And that's kind of what was done in this way. Regardless, we get 480 different ways. Number 4, consider the digits 2, 3, 5, 6, 7, 9. If we can't repeat, how many 3-digit numbers can be formed? 3-digit number, so kind of straightforward. 6 choices, 5 choices, 4 choices, 120. You will often see a lot of these common kind of numbers appearing just because we're using some reasonable amount of choices to pick from. But this gets, of course, in part B, this gets a little more complex. So how many of the numbers in part A are less than 400? So how many of those 3-digit numbers are less than 400? Well, if it's less than 400, and if we're talking about This is not the number 654. Those are numbers of choices. So we could have had the number 562. We could have had the number 736. We can make all kinds of different numbers from those 6 digits. How many of these are less than 400? That's what part I is getting at. And how do you know if a number is less than 400? Well, that first number right here has to be less than 4. So there's our restriction. In other words, it's going to be a 200s number, or it's going to be a 300s number. This 2 represents that this number is either going to start with a 2 or a 3. So another way of writing this is we could have just written this as our restriction is this either needs to start with a 2 or a 3. Once we've picked that numbers, how many do we have left to pick from? There were 6 in total. So now we have 5. Even if we picked a 2, we could still have a 3 to choose from. Even if we picked a 3, we could have had a 2 in the rest of our number. So 5 choices for the next number, 4 choices for the last number. Multiplying this out gives us 40. How do we know if a number is even? A number is even if the last number is even. So this could have been a 2, could have been a 6, and that's it. There's no 4, there's no 8 in this question, and so there's no 0 in this question, so that it can only end in a 2 or a 6, so we have 2 choices for this one. Now we go in and fill in the rest of the question. This ends up being 5 choices for our first number now, 4 choices for the next number now. Also 40 different even numbers. Odd numbers, how many odd numbers could we make out of these? Now, a couple different ways of looking at this. Again, quite simply, this last number can be a 3 or a 5 or 7 or a 9. So we actually have 4 choices for there. Once you've made your choice, you still, out of 6 numbers, 1 number is gone. So this is a 5 choices, and then 4 choices for this last one. We multiply this together. This gives us 80 different odd numbers. Which brings us to a interesting concept in this chapter, and this question involves this idea of compliment. Not a compliment, like you're being nice to somebody and saying, "Oh, you look nice today. That's a lovely sweater." This is compliment with an E here, and it's this mathematical idea that all of the odd numbers and all of the even numbers, those pretty much are all of the numbers all together. So they should add to 120. 40 and 80 are complements of each other, because if it's not even, it's odd. And if it's not odd, then it's even. And so we could have done this question by knowing I had 120 numbers in total that I could make. 40 of them are even, therefore 80 of them are odd. So this idea of subtracting from the whole. Here's your whole group of numbers that you could be make. We subtract the ones that aren't odd, and it gives us the ones that are odd. This idea of complement we will revisit a number of times in this unit. Multiples of 5. If a number is a multiple of 5, it either ends in a 5 or a 0, but we don't have a 0. So it's just this. Times 5 times 4. So deal with the restrictions first. 20 of our numbers will be multiples of 5. Number 5. How many arrangements of any number of letters can be formed with the letters MATH, M-A-T-H? This ends up being 4. If we use one letter, sorry, delete, delete. So in question number 5, how many arrangements of any number of letters can be formed from the letters, the word M-A-T-H? So now we need to look at specific cases of this, because it doesn't tell us if we want 1-letter words, 2, 3, 4-letter words. So we have to add all of those cases together. If it's a 1-letter word, and I know these aren't, it's not a word. You don't have a word of T or H. But we are, for intents and purposes of what we're doing here, when it talks about a word, it's just an arrangement of the letters. So we have 4 different 1-letter words. If we've got a 2-letter word, this ends up being 4 for the first letter, 3 choices for the second letter. Right, is TM a word? No, I suppose it isn't, but let's consider that. When we look at cases, again, when we are looking at this can happen, or this can happen, or this can happen, we are going to add those cases together. 3-letter words, there's 4 times 3 times 2 of them, and then 4-letter words, there's 4 times 3 times 2 times 1 of them. We add up all of those pieces together, get 64. Six, determine the number of odd numbers less than 5,000 that can be created only using the digits 2, 3, 4, and 5, and the digits can't repeat. So we're only using the digits 2, 3, 4, 5. So we either have a 1-digit number, we can use any of those, 2, 3, and 4, and 5. If the digits can't repeat, 2-digit numbers, 4 times 3. 3-digit numbers, 4 times 3 times 2. And then for a 4-digit, it has to be less than 5,000. So we need to be careful in this step that if it has to be less than 5,000, if we're putting these numbers together, this can't be a 5. Then that number would be more than 5,000. So it can be either 2, 3, or 4. So we have 3 choices, and then 3, and then 2, and then 1. Adding this all together, this ends up being 4 plus 12 plus 24, 12. No, it's not. It's 18. My bad. Adding that all together is 58. So in this question number 7, how many even 3-digit numbers can be formed using the digits 0, 1, 2, 3, and 4 when repetitions are not allowed? There's a few things that are going on here that we need to be careful of, and these are kind of common in questions with permutations and combinations. Commonly, we will see this, that if we've got a 3-digit number, it can't start with a 0, because the number 032 is not a 3-digit number. That's a 2-digit number. It's just 32. And so if that's a restriction, that first number can't be a 0, we have to account for that. We also have to account for the fact that if we have an even number, even numbers end in either a 0, 2, or a 4. The fact that 0 is included in that is going to affect how many choices that we have for our first number. So we have to do this separately. We have to look at numbers that ends if this number ends in a 0 or ends in not 0. So if it ends in a 0, we only have one choice for that. If it ends in a 0, then how many choices do we have for our first two numbers? Well, this can be a 1, 2, 3, or 4, 1, 2, 3, or 400. And then once we've selected that, because repetitions are not allowed, this now ends up being how many digits are left? There are 3 digits left. So it's 4 times 3 times 1. We are going to add that to the case where if it ends in a number that's not 0. What numbers are not 0 that are even still? Well, that means it ends in a 2 or a 4. So we have 2 choices for that number. But in this case, we have to be careful here. How many choices do we have for this first digit? It can't be a 0 because that would now be 000, and that's no longer going to be a 3-digit number. It can't be whatever even number it ends with. It can't be that 2 or that 4 that we've already selected. So we only have 3 choices for that digit. It can either be a 1 or a 3 or the other even number, 2 or 4. Once we've sat that number down, now we have 3 choices left for that middle number. We add this all together. This ends up being 12 plus 18 gives us 30. Permutations without restrictions. So our next question introduces a some new terminology and some new notation. How many ways are there to arrange 6 different books side by side on a shelf? Does order matter? So we would think, okay, we've got 6 books. Ends up being 6 books, and then you have 5 choices left for the next book, and then 4, and then 3, and then 2, and then 1. Does the order matter is kind of a critical question in this unit. Does it matter that we are, what order we put these books in? These books, there are 6 different books, and if it's asking us how many ways there are to arrange them, the fact that we are using the word arrange in here kind of infers that it does matter. I multiply this out, this ends up being 720. How many ways can we arrange 50 books on a shelf? Well, this would be 50 times 49 times 48 times 47, and we're going to do this until we get down to 3, and 2, and then 1. This ends up being this huge, massive number, and it would take you a long time to do on your calculator. And so because of that, we actually have a new notation. This is called factorial. How we write this is we would write this as 50 exclamation point. And this is read 50 factorial. This number 720 is 6 factorial. And you would just read it like that. Our mathematical definition of what n factorial is it means it is this number n multiplied by 1 less than n, which is n minus 1. 1 less than that, which is n minus 2. And you're going to keep going down. These 3 dots infer that this pattern repeats until we get to 3 times 2 times 1. So that is our definition for factorial notation. As a side note, it should be stated here that 0 factorial by definition is 1. And we're going to get to that soon enough about why that is, because that seems really weird. Because if n factorial just means you're going to multiply by all of the natural numbers less than it, 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. When do you stop? Well, when you get to 1. So how does 0 factorial make any sense? You'll see. We'll come to that in a minute. We can do this on your calculator. If you have a Casio calculator, you're going to push the button that says Option, OPTN. And then you're gonna hit the F key that says probability, PROB. And we should have one of our, I think it's F1 on all the different models of Casio. And that will give us, it tells us X in factorial. On a TI calculator, we do something kind of similar. You push the button that says Math. And then you go over to the right till you get to the tab, till you get to the menu called probability. And then you'll have a button for factorial. So on the TI calculator, you'd have to type in your number first and then go through those steps and find your factorial button. On your Casio calculator, you can find your way to that tab. You hit 9 and then you hit your X factorial button. We end up with 9 factorial. These numbers get really big really quick. 9 factorial is 362,880. Ten factorial over 7 factorial. We could calculate each of those and divide it all out. And you get 720. But there's more to it than that. And kind of what relates to what we're going to be doing in this section is the fact that instead of calculating out 10 factorial and then calculating out 7 factorial, this is actually doable in your head. Because 10 factorial is this. Now, how can this be calculated in my head, do you think? Because 10 factorial means this. And if I'm dividing by 7 factorial, that means this. And the reality is a lot of this divides out. And so 10 times 9 times 8. 9 times 8 is 72. Times 10 is 720. Very doable. So in question 3, an algebraic question like this, we start to expand the larger of these two numbers. So n factorial divided by n minus 2 factorial, which is larger? N is larger. And so we start to expand this. We start to write out its definition. Now, how far do I need to go? I'm going to keep writing this out, n minus 2, n minus 3, n minus 4, n minus 5, and I'm going to keep going, except for the fact that this ends up being n minus 2 factorial in the denominator. So I'm actually not going to write it out that far. I'm actually going to write it out till I get till here, n minus 2. Because n minus 2 factorial is as far as I need to go, because that can divide out. Now be careful that when we are canceling and when we're dividing this out, we can't do this. That doesn't make any sense. What we are dividing is we are dividing out n minus 2 factorial with n minus 2 factorial. And this leaves us simply with n times n minus 1. In question number 4, we start to expand the larger of these two, n plus 3 factorial or n factorial. The larger one is n plus 3. We go down 1 from that, that's now n plus 2. N plus 1, n, and I could keep going, but I'm not. I'm going to put a factorial on that n to signify that that would keep going. And I'm dividing this by n factorial. That divides out n plus 3, n plus 2, n plus 1. So when we talk about a permutation in this course, a permutation is an arrangement of a set of objects in which the order is important. So we will often see this word associated with a permutation question. And we have a formula. This ends up being on your formula sheet, and it ends up saying this, that if we have n different objects, taken r at a time, where r is less than n, this ends up being n factorial over n minus r factorial. Our notation for this is a subscript of n, capital P, and then a subscript of r. This shows up in your calculator in the same place that we just found that factorial notation. So on a CASO, you use option, and then probability, I believe, is on the next screen. The TI calculators, you hit math, and then you arrow over to probability, and then you'll see NPR. You'll need to type in your number first. So if we are doing 10P3, you would type in a 10, and then you would hit your NPR button, and it on a TI, it would show up like this, and then you would type in 3, 10, NPR, and then 3. Algebraically, numerically, what would that give us? That would give us 10 factorial over 10 minus 3 is 7 factorial. So that's the one that we just did above in question number 2. So, example 1. How many ways can the letters of the word vagina be arranged? The fact that it's arranging these letters, does the order matter? Yes, it does, because it's an arrangement. Now, whether or not we're using your NPR formula or not, this is still a permutation. This is what we did before. We have 1, 2, 3, 4, 5, 6 letters in the word vagina. And so this really just ends up being 6 times 5 times 4 times 3 times 2 times 1. This is 720. So you don't necessarily need to use that new formula. But if you wanted to, this is what's happening here. We have 6 letters, and we are permuting or arranging 6 of them. So this is 6p6. If you push this into your calculator, it will give you 720. If we run this through the formula, this would be 6 factorial divided by 6 minus 6 factorial. Now, this ends up being 6 factorial in the numerator. Downstairs, this ends up being 0 factorial. Now, but our answer is 6 factorial. So a few minutes ago when we said that 0 factorial is equal to 1, that is why. Is because if we have 6 factorial and I'm dividing out the fact that I'm taking all of my letters and arranging them, I'm leaving no letters not arranged. So this ends up being 6 factorial divided by 0 factorial, which is the same as 6 factorial because it's 720, and that's it. How many letter arrangements, 3 letter arrangements, can we use from the word graphite? We count this up. Graphite has 1, 2, 3, 4, 5, 6, 7, 8. Does the order matter? Yes, it does, because it's an arrangement. We can do this way, and we could think, okay, I've got a 3-letter arrangement. It is 8 letters, and then 7 letters, and then 6 letters. We are arranging that infers that they're Scrabble tiles, that we're not repeating letters. We can't have repeats if we are arranging the letters. So this ends up being 8 times 7 times 6. This ends up being the same thing as this notation is 8p3. We have 8 objects and we're permuting 3 of them. That ends up being the same as our formula says 8 objects means n is 8. If r is 3, then this is n minus r. That's 8 minus 3. Makes this 8 factorial over 5 factorial. If I'm writing that all out, 8, 7, 6, 5, 4, 3, 2, 1, all multiplying, divided by 5 factorial, which is 5, 4, 3, 2, 1. Most of it divides away. What are we left behind with? This 8 times 7 times 6. So we get the same thing either way that we look at it. This ends up being 336. So a little bit of algebra that we're going to do here. Solve for n in the equation. np2 is equal to 12. Well, np2 is n factorial divided by n minus 2 factorial. This is equal to 12. Expanding that numerator, n times n minus 1 times n minus 2. And I could keep going, but I don't want to because n minus 2 factorial is what I have downstairs. And this is equal to 12. N times n minus 1. Subtract 12 from both sides. N squared minus n minus 12 is equal to 0. We factor. We have 2 answers. N is equal to 4. N is equal to negative 3. This answer is extraneous. We can't have a negative number as a factorial. We can't have negative 3 factorial. And if you think about how factorial is defined, that makes sense. Subtract negative 1. You subtract 1 from it, you get negative 4 times negative 5 times negative 6 times and it doesn't end. So therefore, that doesn't work. N equals 4 is our answer. So n is equal to 4. N equals negative 3 is extraneous. As factorial is undefined. For n less than 0. Now, this whole idea of explain, so on your diploma exam, they would expect a fair amount of detail of showing your understanding of what's going on. It's why a question like this isn't just state what your answer is, because you could jump into your calculator and pretty quickly figure out that 4p2 is 12. They're wanting a little more detail about why that's the only permissible value of n. Number 4. Pretty similar, but a little more complicated algebraically. Determine the extraneous root in the solution of np4 is equal to 28 times n minus 1 p2. We have n factorial over n minus 4 factorial equal to 28 times n minus 1 factorial over. Now we have n minus 1 minus 2 within this factorial. We can start to simplify this out. This ends up being n times n minus 1 times n minus 2. And this is going to be ugly if we're going to have to multiply it all together. I'm going to stop writing it as n minus 4 factorial, so that's going to divide it with your denominator. This is equal to 28 times n minus 1 factorial. Now, what do we have downstairs in the denominator? That actually ends up being n minus 3 factorial. So when I divide that out, I'm left with this. N minus 1, n minus 2, n minus 3, and everything less will divide out. Now, we have both on the left side and the right side of this equation, we have a factor of n minus 1, and we also have a factor of n minus 2. So really this question starts to melt down quite nicely, that on the left side, n squared minus 3n is equal to, on the right side, 28. Whew. N squared minus 3n minus 28 equals 0, and minus 7, and plus 4 is equal to 0. Therefore, n is equal to 7, and we should probably explain that n is equal to negative 4 is extraneous. N is equal to negative 4 is an extraneous, as negative 4 factorial is undefined. Hint, if you end up with a polynomial with a degree greater than 3, something's gone wrong, because you're not going to be asked to do something that complex that you'd have to multiply all of this stuff together. So we divided that out. It simplified what we had here really quite nicely, and that ended up being it. And on that note, good luck, and if you have any questions, please ask, and see you again.